So let us consider the equation. Say this is 1 square plus 2 square plus 3 square dot 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 up to x square. So we will form the condition that this is equal to another variable which is y square. Right? The particular condition here is that I need a square as my answer. The y which I'm going to write there should be a perfect square. Let's say. Okay. Now, in mathematics, we already have studied this, right? This summation is a standard summation, that is 1 square plus 2, a square of all the, sorry, sum of all the squares up to a term n. We already have studied. We have the equation in terms of n. Let me convert that. This is x into x plus 1 into 2x plus 1 whole divided by, I think, 6. Right. Okay. So what we'll do now, let's try to simplify this, because I want to initially show that this is a cubical curve, right? From that I will try to derive whatever I need concepts. Right. Okay. I think this comes to be, let me see. I think we have one. The we'll relate that y equal to x later, I guess, because right now I need to show that this is a cubical curve, right? So I'll take the 1 by 6 into x as it is. Then if I multiply, I think I'm going to get 2x square plus x. I have kept the x outside. There is another 2x plus 1. Now I think I'm going to get that. So this is 1 by 6 times, I think 2x cubed. Then this is 3x square plus x, right? Okay, by 6. So now I'll apply the 1 by 6. If I multiply inside, this becomes 1 by 3 x square plus this is 1 by 2, not x square, my mistake. This, the first term is x cube, sorry. Yeah, so this is x 1 by 3 x cube 1 by 2 x square plus 1 by 6 into x. Now you can see that this y square is a cubical curve, correct? 1 by 3 x cubed plus 1 by 2 x square plus 1 by 6 into x. Right. Now this actually is an example, okay, of elliptical curve. Now if you look carefully, we understand the other aspects as well. So first thing, this is, right, a cubic equation. Now since there is a y square, right, that's the term which helps us in understanding that it is a symmetric. Y square, I'll come to that point. So this is symmetric about whenever you have a power of one of the term, like either x or y exists, right? Then that means it is symmetric about the other axis. If you have y square, it means symmetric about x axis. I'll tell you why. Okay, symmetric about x axis. Now let me justify this. So when I calculate, if at all I try to calculate the y value, this is because, I'll just write in bracket, because, say, what is y? Y is equal to square root of that term, right? 1 by 3 x cube plus 1 by 2 x square plus 1 by 6 x. Whenever I take a root, and I'm definitely I'm sticking to the real numbers, right? Real, in the sense the normal xy plane, I'm going to get two roots, right? Plus or minus. Yeah. So for every x, there are two values of y. Correct. This is what is the meaning, right? If I have a curve, for every x value, I have two roots, plus 2, minus 2. Correct? Which means it is symmetric. Next, for a next point x-axis, I have another point here, a similar point on the other side. Right? This is what makes the curve symmetric about x-axis. So when you have a y square term, it means symmetric about x-axis. Okay? From the basics, right? So also this is not an ellipse, right? So normally we get confused whether elliptic, since the term comes as elliptic, is it an ellipse, right? It's not ellipse. Okay, so let's just keep that in mind. I'll proceed further. So now let's say what is the specific feature that we are looking here is actually derived from one of the standard mathematical procedures. It's actually called as method of Diophantus. If you have right, have you heard of that? Oh, all right. Okay, fantastic. Okay, all right. So I'll just brief you about that. It's actually one of the technique in which, using which you can, if you note any 2 points on a curve, you can find the third point. Right? That's what is called as method of Diophantus. So let me write that here. So this is the method of DIO, I guess. DHAN. Correct? Okay. So this is method of Diophantus. You normally anyway, whenever a equation is given, irrespective of what equation it is, right, it can be right now it is for elliptic curve, but in general any curve you take, 2 points means third point you should be able to find out. That's what is the basic idea here, right? Using known points, finding out the unknown points. Okay, so let's start with the same curve which we have written so far, right? I think the y square, let's consider that. So I'll try to get the points now. So I think this can be written as x into, I'll write the both formats, okay, so that it becomes easier for me to calculate. It is 2x plus 1 by 6 was the first equation which we directly wrote. Then we wrote the other format, that is 1 by 3 x cube uh, plus 1 by 2 x square plus 1 by 6 x. Okay, now let us verify whether both sides will match for some standard functions or standard values of x and y. Let me assume that x is equal to 0. Okay, so if you put x equal to 0 on the right side, left side becomes 0. So one answer is 0 comma 0. Correct? 0 comma 0 is one answer. And let me check with the standard. Let me put 1, right? If y is 1, 1 square is 1. Right hand side, 1 into 1 plus 1, 2. 2 into 1 plus 0. So 3 by 6, that's also is an answer. Correct? So I can write this, and 1 comma 1, right, are the roots, I can say. Now, okay, I think this is why you told y equal to x, right? So you see here, right, the one line which passes through both of these points, correct, is y equal to x, right? 0 comma 0 means y is equal to x. 1 comma 1 also suggests that y equal to x, right? Okay, okay, so y equal to x is the straight line passing through uh, them. I'll write, okay, that's correct. Now you can say that yes, in order to find out the, since it is a what do you call, it's actually an equation of degree 3, right? It's a cubic curve. When you solve any cubic equation, how many roots you are expecting? 3 roots, right? So let us use that now. So y equal to x line should also pass through your third point, correct? Right, so that's our very basic idea now. So let us solve these two equations to get that. Okay, then this makes sense. Okay, so I'll write let's try to find the third point by using the simple algebra. Okay, so I would like to calculate the intersection. Okay, intersection of my first curve. What is the first curve? First curve is y square is equal to 1 by 3 x square plus 1 by 2, not x square, sorry, this is x cubed, plus 1 by 2 x square plus 1 by 6 x. This is my first term. And the y equal to x. Okay, so how do you solve this? You make y square is equal to x square, right? So this implies x square is equal to, right, the right hand side that is already present, that is 1 by 3 x cube plus 1 by 2 x square plus 1 by 6, I guess. Correct. Okay, now what happens when you simplify? Take the x square to the other side. So this means it is 1 by 3 x cube. So 1 minus 1 by 2. So this is minus 1 by 2 x square plus 1 by 6 x is equal to 0. Okay. Okay, I can solve this. I don't have to go with the calculator. I think I can solve this easily if I have a x cube present. So what you do, you multiply by 3. That means it is x cube minus 3 by 2 x square, I think, plus half x equal to 0. So you see, for this given equation, we have 3 roots. Okay, so easily you can find the all the 3 roots out. Sorry, out of which 2 are known to us, right? Okay, so solution is straightforward. So from the cubical equations, I'm writing this. We already have studied somewhere long back, I guess, in mathematics, that if you have a cube equation, what is very interesting for us is this number, the coefficient of x square. So what I do, it's negative of that coefficient, that is minus 3 by 2, minus of minus 3 by 2 is equal to first root. First root is 0. What is the second root? Second root is 1. Plus the third root, which is unknown to me, that is x. I don't know the third root. So you remember this point, right? Okay, so it's like this. I'll repeat. So coefficient, the basic condition to apply the this particular rule is that I cannot apply to this because it is 1 by 3 x cube. So it should be proper x cube only, 1 into x cube. I should bring it into that format first. So you see here, I brought it into that format, multiplying by 3. This 1 by 3 is eliminated. I have a 1 here. I have to have this condition. Okay, so in this condition, I take the coefficient of x square and negate that. If it is minus 3 by 2, this becomes minus of minus 3 by 2, which is plus 3 by 2. Okay, equal to the sum of your roots. 3 roots you have, right? First root, that is the rule. It's a rule from we have derived in the basics that the sum of your roots is equal to the negative of the x square coefficient. Okay, this is one rule, right? It's very useful to solve the cubical equations, right? You don't have to keep solving the whole equation. Simply you do this, you get the answer. Okay, no problem. So this is 3 by 2 minus 1 is equal to x. So my third root becomes equal to half. You see? Straightforward. So I know this. So since this is present on y equal to x curve, that y is also half. Minus half? How? No, y equal to x line, correct? Right? So y equal to this means the coordinate of the line, coordinate of the point is, right, 1 by 2 comma 1 by 2. So we have 3 points now, correct? So the first point is 0 0, next point is 1 1, and the third point I found is 1 by 2 comma 1 by 2. Okay, and yeah, what you told is actually right. And the other point, because of symmetry, symmetry of curve indicates that my next this will be 1 by 2 comma minus 1 by 2. Right, I got a new point. Right, so this same concept can be extended further. Right, what you do, you can say, let's form another line. Right, so another, that is straight line through, maybe the point I consider is 1 comma 1, which is one of the root, and the other root which we just calculated, 1 by 2 comma minus 1 by 2. Possible, correct? So let's try to write this. What is the equation of this? It is y minus y1. So y minus of minus half is y plus half divided by x minus x1. x1 is half, should be equal to, I think this is y2 minus y1, 1 minus minus half, and this is 1 minus half. correct? So right hand side is simply 3 by 2 by 1 by 2. So 2 cancels. This is 3 by 1. So this means I cross multiply. That means uh, common denominator first I'll take, that is 2y plus 1 whole divided by 2 whole divided by, this is 2x minus 1 whole divided by 2 is equal to 3 by 1. So 2 cancels. I can write the equation, I guess 2y plus 1 is equal to 6x minus 3, right? So this implies what is this? This term, see this term I am taking a common denominator, right? Same thing happening with the denominator as well. So 2x, right? Okay, so this means I can write 2y is equal to 6x minus 4 plus 1 going to the other side. I think I have the equation of the straight line is y is equal to 3x minus 2. This is the equation, right, which connects the 2 points which we considered. Right. Just now we have seen that if you draw a straight line, you should get a third point. Correct. So let's do the same thing once again. That is intersection of my equation. That is y square is equal to what is that? I think 1 by 3x cube plus 1 by 2x square. 1 by 6x and this line. Okay, right. Okay, so that means I should take a square now because I need a y square, correct? So on one side, true. So what is a y square? Okay, I'll write this term first. 1 by 3x, this is a y square, plus 1 by 2x square plus 1 by 6x. This is equal to, let's square the other term, that is 3x minus 2 the whole square, y square. Okay, I'll expand here itself. This means this is 9x square, correct, plus 2 square, so 4, minus 2 into 2 into this, so 12x, correct. All right, so let's bring everything to the same side. I have a 1 by 3x cube, then I have 1 by 2 minus 9, so 1 by 2 minus 9 should be minus, I think, 17 by 2, okay, into x square. Then we have 1 by 6 x plus 12x, so 1 by 6 plus 12, 72 plus 1, 73. So this should be plus 73 by 2x, and we have a plus 4 coming to the other side is minus 4. See, this is a cubical equation which I get now. Right, once again I need to solve this, but it's easy if you multiply by 3, right? So because my condition is that I should have a proper cube, so this is multiplying by 3, I'm going to get 17 3 is a 51 by 2 x squared, then plus 219 by I think that is, oh sorry, this was a 6, my mistake, this is 6, right? Where? Oh, they are solving the whole thing, same to same. Oh, is it there? No, no, I didn't. I was just asking. Do you have the whole solution with you? This thing they are already solved. Oh, is it? Okay, that's good. Okay, then I am doing right, correct? It's matching. Oh, okay, obvious because I told right. I just need this point to solve this question. I need only this point, right? That is correct. Minus of minus 51 by 2 is equal to, you know, the 2 points, correct? The first point is a half, second point is 1, I need the third point x, right? So correct, so this implies, I think, let's calculate, x is, sorry, x is equal to 51 by 2 minus half minus 1. correct. So this means 51 by 2 minus this. 25 minus 1 is 24. X is this. This implies I can calculate. Okay, y is equal to, this is 3x, 3 into 24 minus 2. 72 minus 2 is 70. Right, so you see you got a point now. So this implies the new point, right? New point on the curve, right, is 24 comma 70, right? Okay, that's how. So we can solve this and we can keep going ahead, right? So you see that this is a very basic idea of the what you call as a elliptical curve, right? You have 2 points, right? Connect the 2 points, you should get a third point, right? And the it means 24 comma minus 70 is also a point, right? Hmm. Right. So this means, okay, to that question which you had asked earlier, right? That is how many number of total squares are required. I think 70 is a possible answer because 70 square is 4900, which is a perfect square, right? Right. So because of that, you can say that, yes, this is the answer. Okay, so now let's move ahead. Now I'll consider a different function. Let me say that, okay, uh, let's make sure that we will come to a definite specific set of integers only. We'll deal with specific set of integers because that's what is the application of this elliptic curve when it comes to the cryptography, right? Right, I'll deal with the only those things of elliptic curves which we use in cryptography later. Okay, right. So consider one example. Let's say that actually I wanted to start from here, right? So if you consider another equation, this is another standard EC elliptical curve. Y square is equal, I'll come to that in the general format, but let me define. So because plus 2x plus 3, let me write in this way, right? And I write a mod operation here. This is, I'll define mod 5. Now you keep substituting different values of x to this. Okay, so put x equal to 0 because I have only options like x equal to 0 is a possible case. I can put x equal to 1, I can put x equal to 2, I can put x equal to 3, and I can put only till x equal to 4 because x equal to 5 is under mod 5, it is 0 already, it will be considered. Right, now you calculate what is the y square. When you put x equal to 0, y square is equal to 3. Right. So in mod 5, do you have an answer? Do you have an answer which satisfies this condition? Right? Is my question. Right? I'm basically looking at the only finite set of integers. I can, my answer could be only integers. I cannot move outside this. In the sense, when you say y square is 3, I have an answer saying that y is equal to root 3. And root 3 is lesser than 5. You can say that this satisfies the mod condition. Correct? Because the y is equal to root 3 is a solution. But you see, I'm considering finite set of integers. Right? Because as we know already, we can define the elliptic curve in any domain, any field. Correct? Yeah. Right. So this means what is the answer? In the sense, if you put y is 4, that should satisfy this condition. Correct? So if you put y is equal to 4, y square is 4 square, that is 16. Correct? 16 mod 5 is 1, not 3. So for example, you said y is equal to 4 is an answer, right? So this means y square, 4 square is 16. I should take a mod 5. No, we'll come to x equal to 4. Right now we are dealing with x equal to 0, right? So x equal to 0, I come to an answer that I put x equal to 0 in the above equation, I get y square equal to 3, right? My question is, what is the value of y which satisfies this condition under mod 5? Is there any answer? I don't think so, because y square equal to 3 gives you an answer, y is equal to root 3. It's not a answer in integer, that's all. If you consider real numbers, yes, there is an answer, but now I am considering the set which I can find answers is only integers, right? So this means you see that there is no solution. Okay, let's put x equal to 1. What happens to y square? This is 1 square plus 2 into 1 plus 3, so I think that is 6, right? But 6 is actually, I should apply the mod 5 operator, that becomes equal to 1. Now can you tell me, can you check, is there any answer? Y square, for some values of y which is lesser than 4, more greater than 0, right? The answer becomes 1, y square. So take 1 as an answer. 1 square is 1, it is true. So y equal to 1 is an answer, correct? Also take 4. 4 square is 16. 16 mod 5 is once again 1. So 1 and 4, y is equal to 1 and y is equal to 4. Are you okay? We have two answers in this case. Let's put x equal to 2. When this is the case, what is y square? 2 square plus 2 into, is it 9? Okay. Okay. Another answer, right? Okay, I think, sorry, I made a mistake, right? Please excuse me. See, this is x cube, sorry. Previously we didn't, because it's a cubical curve. My mistake. Sorry. So now let's calculate that. 2 into 2 into 2 plus 4 plus 3. I think 15 now. Correct? Previously we didn't observe because it's 1, right? 1 and 0, so didn't matter. So mod 5. 15 mod 5 is 0, right? So we have one answer, that is y equal to 0. Y square is 0 means y is 0. I got this. So x equal to 3. Y square becomes equal to 3 into 3 into 3. 27 plus 6 plus 5. Okay, this is actually 36, correct? Mod 5. So this is 1. So y square is 1 means once again I have y is equal to 1 and 4. Then x is equal to 4. 64 plus 8 plus 5. 75, right? This is 75. I have to take the mod 5. What is the answer? Mod 5 is 0, right? So this means y is equal to 0. So now you see, if you put the x value starting from 0, 1, 2, 3, 4, for it's a curve, correct? Yeah. If you put those x values, I get the given y values, right? So I would like to put it in this way. This implies the points on this curve. This curve, in the sense, the y square is equal to the one which we consider, okay, x cube this. So make the pairs of that. When x is equal to 0, there is no solution for y, in the sense 0 comma 0 is not present on the given curve, okay? There is no origin is, it's not passing through the origin. That's the first point, right? Then I go to x equal to 1. X equal to 1 means I have two answers. My curve passes to 1 comma 1 and 1 comma 4. Then x is 2 means it's going to pass with 2 comma 0, right? Then it's passing with 3 comma 1 and 3 comma 4. Then it's going to pass with through 4 comma 0. See, this is how we are, right? Now we understood that if I restrict my curve to have only the integers, only these are the points, correct? These are the points through which it can pass. It means it will not pass through any other points, though when we draw, you can actually see that, okay, if I try to draw this, let me try to draw first, right? If at all I try to draw this, maybe, right, I know that I may draw something like this, maybe, okay? but you see it's actually passing through only the very specific points, 1 comma this, maybe 1 comma 4 will come somewhere here, to and let's say the different points are there, but the condition is that the values are only integers, correct? Only integer value can come. This means now we have a, because why we are looking at only integers is that, see, when we try to represent a number, right, for cryptography we are expecting it to be an integer, right? The keys which you enter, etc., are always the integers only. It's easier to deal with integers rather than dealing with any other fractions, correct? So that's why I started with the concept of integers. Now this makes, if at all you consider this kind of system, right, this implies all the points on the curve are discrete. This is discrete, right? I have 1 comma 1. It's not continuous. I don't have 1 comma 1.5. That's not there. 1 comma 1.111 is not there. After 1, correct. So it's discrete, which refers to only the fixed points. Correct. This is the first point which I understand from this. This is what I need for cryptography. Okay, then actually this condition, the specific condition, is what is a standard term in terms of the cryptography, specifically related to the elliptic curve. It's called as, you might have heard, or it's there in the document which you shared. This is ECDLP. It is EC for same elliptic curve, discrete logarithmic problem. Okay, right? I think you have heard that, right? So easy, in this, since this is the discrete points are, since we are considering only the discrete points for our analysis, right, this leads us to a different problem called ECDL. We'll see that later, okay, when we start with the exact cryptography point. Okay, now since I defined you what is the condition and what we need when we consider a elliptic curve which is of a cubical order, right? Now we'll come to the EC required for EC required for cryptography. Okay, so in this, let us say if you try to define this as f of x comma y equal to 0, because you saw that this is y square is equal to x cube plus something, right? You bring it into the same side. You can move the x terms to the other side, and we can call it as equal to 0, right? So that's what I call it's f of x comma y, right? Normally this is expected to be a, already we know that it has to be a cubic curve now, right, on a given field. Now we define the mathematical terms, say k. Okay, any field k, right? This k should be, specifically I'm talking about the cryptography term, it has to be, I think I answered this question earlier, it has to be a prime or it has to be binary. This is the very basic condition for the cryptographic elliptic curve. For example, you define the field. Field is defined as FP, standard mathematical notation, right? This is the prime field. Number prime numbers. Normally, for elliptic curves, you take this prime value p greater than 3. Okay, just for your reference. Then the binary field is defined as f2 to the power m. Okay, this is something like all the binary numbers with 2 to the power m elements. For example, if you take m is 2, this is 2 to the 2, there will be 4 elements, 0 0 0 1 1 0 1 1, right? It's in that way. Perfect. Yes, 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 correct. So that's why we specifically are looking for the all those fields which generate my discrete numbers. Okay, whichever systems can generate discrete events or discrete numbers, you can use it over here. So the most common ones and easier to understand and easy to build applications is, one is prime field, one is the binary field. So because of that, we are using this in the cryptographical elliptic curves. All right. Okay, so there are several varieties of curves which we can build using this. So now I go for the general form. There is actually a proof for this, but anyway, let's skip that. That's actually too mathematical. I don't want to go that much in depth. Okay, so generally I'll write y square is equal to, this itself has been mentioned even in the document, so I'll directly write it. Okay, so let me know if you want any proof for this. I can do that, but as of now, I think it may not be needed, right? Because this is the standard format. All right, x cube plus ax plus b. uh, Yeah, actually there are several options, right? Using which I think one of the answer is what you told, right? You can start with our very basic equation. There is what is called as a general form of what you call the elliptic curves, okay, which actually have the terms containing uh, say y square plus, this is something like, maybe I'll write a times x plus maybe b is equal to x cube plus something like, say, okay, a dash into x square plus b dash into x plus c. Maybe it is in this format. Okay, this is the general format of a uh, elliptic curve, general. This is actually, by making some substitution, you can bring this into this format. That's what is the normal derivation. Okay, right. You will prove that this can be brought into this format, right? So nor then they are calling this as, this part is the general equation of the elliptic curve. This is what is the proof, right? Many methods do exist to prove that, right? It's a mathematical derivation, that's all. Yeah. Correct. We can use that, right? They are giving the proof by using the real example, right? It's a mathematical. I need to do some changes in this equation. I bring the terms containing x to the same side, then I make an assumption, right? Then I prove. It's a mathematical steps, right? It's not with any specific numbers. That is applicable for everything, right? So right, I can definitely prove this is equal to the above equation. Y square can be written in this format, right? And that's what we call as the standard equation of a elliptic curve. Okay, fine. So but anyway, we are using this directly, so I don't think that proof is necessary. Okay, but if at all in any later stage, if you feel that I need to know that, you let me know, I can do that. Okay, right. Otherwise I will stick to this equation. Y square is equal to uh, the x cube. It has to be a cubical function, that's why x cube plus, I don't need a square term, I need a x square. The a will take care of the actual square term in the derivation. Okay, plus b. This is the one form which we are looking for. Now, I come to the specific case that I define this particular elliptic curve, right, over say any field, over a field, right? Say field is denoted by L, right? Let's define this so that this becomes easy for you to understand. So E of L, it's a proper set theory notation. E of L is equal to, uh, the textbooks will directly use the infinity here itself, but I will use this, the concept of infinity I'll bring later. But anyway, you know the answer now because why infinity is used. Okay, this is union of this infinity with any set containing x comma y belonging to a L cross L field, right? Because if you are considering the, say, prime numbers, so first 10 prime numbers maybe, okay, then first the L value will be 10 numbers, whatever you can take, and those 10 numbers will be for x and y. So L cross L, L for x, L for y. Okay, so Yeah. Only certain points will, like we consider, just now we consider one example, right? You see that, right? It was a mod 5. My field was mod 5 integers, correct? So L had few values, 0 1 2 3 4. The other L also 0 1 2 3 4, right? Okay. uh L cross L field. Oh, yes, only the discrete points, right? So if you define the, see, here the L is not defined. L is any field. You can take prime, you can take integer, you can take real numbers, you can take complex numbers, anything. But if we want to restrict this to our concepts of cryptography, then yes, L is discrete. Okay, right? Okay. This can be okay. We'll write a format as well, because the same thing is mentioned in the book as well as the references. So y square, it's in this format. That's what they are mentioning. Y square dot 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 can be anything. Okay, x cube plus dot, because it has to be in this format. Only when you have this format, it becomes symmetric and three roots, right? So this is the general format. Okay, now I'll justify now why the infinity is included. I'll just write one point here. Okay, so if at all you draw a vertical line drawn uh, on the curves uh, are expected to pass through the third point, right? Because we know that whenever you draw a line through 2 points, the third point should be obtained, correct? Correct. It's the same point. I'm saying the same thing, but maybe my wordings are different. Okay, so I'll tell you. Right. I'll draw something just to justify this. Let me say. Okay. Say this is the only I draw the first quadrant. Let me assume that there is a curve. Right. Say the curve is maybe something like this. All right. Now, if you consider a straight line, like maybe this is the first example. Okay, I'll change the color. Uh, okay, let's say I'm drawing. This is what we already have proved. If you draw any line, random line, it should pass through 3 roots. Correct? Root number one, right? This is the second root, and this is the third root. This satisfy for each and every line you can draw, except the vertical lines. Perfectly vertical line, let me draw. Okay, let me draw a line that is actually perpendicular, in the sense it is actually something like this. Now you see it will intersect where? Only 2 points, correct? That's the problem, right? My basic condition for cubical equation itself, I need 3 points, right? I need 3 points, but in this case I get only 2 points. Means what? Third point is at infinity. That's the thing. No, this is not tangent. Tangent means only 1 point. Okay, so third point assumed at infinity. Now in mathematics we cannot assume things as this is like this. Okay, I cannot say that simply. I cannot say that okay, there is a point at infinity. This should be validated. I will validate that maybe in the next class. Okay, so though we assume that there is a point at infinity, right? This actually is true. We'll assume initially saying that okay, the third point is present at infinity. That is because your curve is going to infinity. You can see here this will go to infinity. The other side will also go to infinity, right? So since this goes to infinity, I have the authority to assume that okay, maybe there is a point at infinity which satisfies this. That is true, but right now we will simply assume, right? Okay, as of now, but there is actually a proof coming up, right, when we discuss the next points. All right. So